Welcome to this expert-level training module focusing on identifying the features and capabilities of artificial intelligence speech workloads. Welcome to this expert-level training module focusing on identifying the features and capabilities of artificial intelligence speech workloads. Speech is fundamentally one of the most natural ways humans communicate with each other. By bringing sophisticated speech capabilities into our AI applications, we create highly intuitive, accessible, and deeply engaging user experiences that extend far beyond traditional keyboard and screen interfaces. Whether you are building an interactive voice assistant, developing accessible applications for users with visual impairments, or engineering autonomous conversational AI agents, a rigorous technical understanding of speech technologies is absolutely essential. Within the broader AI landscape, enabling this kind of rich interaction dictates that the system must fully support two fundamental capabilities. The first is speech recognition, commonly referred to as speech-to-text, or STT, which is the system's ability to accurately detect, capture, and mathematically interpret spoken audio input. The second core capability is speech synthesis, or text-to-speech, which is the system's ability to dynamically generate natural-sounding spoken audio output from written data. When we leverage robust cloud platforms like Microsoft Foundry and the Azure Speech Services, we gain access to highly optimized, pre-built neural models that manage the massive computational overhead of processing audio streams. By integrating these speech endpoints via dedicated software development kits, developers can bypass the monumental complexity of training acoustic models from scratch. Instead, they can focus directly on orchestrating business logic and delivering value. Throughout this comprehensive session, we will dissect the complex internal pipelines of both speech recognition and speech synthesis. We will explore how raw sound waves are converted into text via acoustic and language modeling, and conversely, how text is transformed into high-fidelity audio using neural vocoders and advanced prosody generation. Let us dive right into the mechanics of speech recognition. While identifying speech workloads is an architectural task, it directly influences how you structure your client application code. Your codebase will be responsible for securely routing raw data, either binary audio streams or UTF-8 text strings, to the highly specialized Azure Speech API endpoints to execute these distinct machine learning pipelines. Speech recognition, or speech-to-text, enables applications to convert spoken language into highly accurate written text. This is not a single, simple operation, but rather a complex, multi-stage coordinated pipeline. The journey begins with capturing the raw audio signal via a microphone or streaming audio file. This raw signal undergoes critical pre-processing, where the system extracts specific feature vectors known as mel-frequency cepstral coefficients, or MFCCs. These features mathematically highlight the distinct acoustic patterns of human speech, while filtering out irrelevant background noise. Once the audio features are successfully extracted, they are fed directly into the acoustic model. The acoustic model, frequently built upon advanced transformer neural networks, evaluates the audio data to predict phonemes. A phoneme is the absolute smallest unit of sound in human speech. Crucially, acoustic models do not recognize whole words. They simply output a massive sequence of phonetic probabilities. Because phonemes are strictly language-specific, a model trained on English phonemes cannot recognize Mandarin tones without complete retraining. However, phoneme predictions alone do not guarantee accurate transcription. An acoustic model might easily confuse homophones, such as there and there, because they share identical phonetic structures. To resolve this profound ambiguity, the system relies on the language model. The language model applies deep statistical knowledge of vocabulary, grammar, and common word sequences to predict the most logical text. It utilizes statistical patterns to know that certain phrases appear more frequently, and applies deep context awareness. For instance, if the audio translates to "I need to," the language model heavily weights upcoming verbs like go or finish, while aggressively discounting nouns. By aggressively layering the language model's grammatical logic over the acoustic model's phonetic predictions, the engine dramatically increases the accuracy of the transcription process. To invoke this pipeline programmatically, developers utilize the Azure Speech-to-Text SDK. Your Python code initializes a speech recognizer object configured with your Azure credentials. When you call the recognize_once_async method, the SDK handles the audio capture and transmission, returning a highly accurate string based on the combined acoustic and language model processing. With both acoustic phoneme probabilities and language model sequence predictions generated, the speech recognition pipeline moves into the highly critical decoding phase. Decoding algorithms must rapidly search through millions of potential word sequences to find the exact transcription that perfectly balances faithfulness to the raw audio signal with grammatical readability. The absolute most common technique used here is called beam search decoding. As the system processes each sequential audio frame, the beam search algorithm actively maintains a strict shortlist or beam of the highest scoring partial transcriptions. At every single processing step, it calculates and extends each hypothesis with the next most likely word, aggressively pruning low-scoring paths from memory and keeping only the absolute best candidates. Once the final sequence is mathematically selected, the raw text enters the post-processing stage. Post-processing is vital for transforming a raw string of lowercase words into properly formatted human-readable text. This includes automated capitalization to recognize sentence boundaries and proper nouns, as well as punctuation restoration, which intelligently inserts periods, commas, and question marks based on grammatical structure and spoken prosody. A highly critical enterprise feature is inverse text normalization, or ITN, which converts spoken formats into written standards. For example, converting the spoken words 3 p.m. into the formatted string 3 p.m., or 1023 into the digit 1023. Finally, post-processing can include active profanity filtering to mask inappropriate words to meet compliance policies. The Azure Speech Service returns this fully formatted transcription alongside rich metadata, including exact word-level timestamps and granular confidence scores, enabling your client application to precisely highlight uncertain segments for human review. When parsing the JSON response payload from the Azure Speech API, your application code can access the detailed metadata generated during post-processing. The payload includes the normalized text string, the masked profanity string, and an array of individual word objects, each containing its exact start time, duration, and mathematical confidence percentage. Observe the decoding and post-processing workflow. Acoustic and language inputs are evaluated via beam search decoding to find the highest scoring sequence. Now we transition to the second foundational capability, speech synthesis, commonly known as text-to-speech, or TTS. Speech synthesis converts written text into natural-sounding spoken audio. Just like recognition, synthesis is a highly complex, multi-stage pipeline designed to build a final audio waveform incrementally. The very first stage is text normalization. Before a system can pronounce anything, it must standardize the raw text, expanding abbreviations, numbers, and symbols into their exact spoken forms. For instance, the string Dr. Smith ordered 3 items for $25.50 is normalized entirely into words. Dr. Smith ordered 3 items for $25.50. This prevents the engine from attempting to physically pronounce a dollar sign, which would cause an immediate synthesis failure. Following normalization, the text undergoes rigorous linguistic analysis. This stage breaks the normalized text down into syllables and maps the written letters, known as graphemes, to pronunciation sounds or phonemes. Because English spelling is notoriously irregular, this grapheme to phoneme, or G2P, conversion utilizes both strict pronunciation lexicons and advanced neural models to accurately guess the pronunciation of unknown or domain-specific words. During this phase, the system also identifies syllable boundaries, marks stressed syllables, and evaluates the phonetic context of adjacent sounds. If the system encounters homographs, words spelled identically but pronounced differently depending on context, such as the present tense read versus the past tense read, the linguistic analyzer evaluates the surrounding sentence structure to lock in the correct phonetic translation. This meticulous preparation phase ensures that when the neural network takes over, it possesses a perfect blueprint of the language semantics. This deep linguistic mapping guarantees that the foundational building blocks of the audio output are phonetically flawless before the system ever attempts to generate the physical sound wave. To execute text-to-speech in your application, you utilize the Azure Text-to-Speech SDK. Your code instantiates a speech synthesizer object. When you call the synthesis function, you pass in the raw, unnormalized string. The Azure Cloud endpoints automatically handle the complex text normalization and linguistic analysis, shielding your client application from this massive computational burden. Having mapped the text to precise phonemes, the speech synthesis pipeline must now determine exactly how to say those sounds, bringing us to prosody generation. Prosody refers to the rhythm, stress, and intonation patterns that make speech sound genuinely human and natural, rather than flat and robotic. Prosody generation relies heavily on transformer neural networks that have been exhaustively trained on thousands of hours of recorded human speech paired with transcripts. These models learn complex vocal characteristics, such as pitch contours, where pitch rises for questions and falls for statements. They determine the exact duration to hold each sound to create emphasis, calculate intensity for volume variations, and inject highly natural pauses between phrases to aid listener comprehension. The model evaluates syntax, semantics, and emotional tone to output a highly specific target blueprint. For example, the prosody output might dictate, produce this specific phoneme at 180 Hz for 80 milliseconds with moderate intensity, then pause for 200 milliseconds. Finally, this rich specification enters the speech synthesis stage, where modern neural vocoders take over. Advanced deep learning architectures such as WaveNet, WaveGlow, and Hi-Fi GAN operate as acoustic models. They convert the phoneme and prosody targets into MEL spectrograms, which are detailed visual representations of sound frequencies over time. The neural vocoder then mathematically transforms these MEL spectrograms directly into raw audio waveforms, typically generating 16,000 to 48,000 discrete amplitude samples every single second. This neural vocoding process achieves incredibly high fidelity, capturing subtle vocal characteristics like breathiness and resonance, ultimately delivering studio-quality, natural-sounding audio directly to the user in a fraction of a second. When generating speech, developers can exert fine-grained control over prosody by using speech synthesis markup language, or SSML. Instead of passing plain text, your Python code constructs an XML-based payload, where you wrap specific words in tags that explicitly dictate pitch adjustments, speaking rate changes, or mandatory pauses, overriding the model's default prosody predictions. Here we see the final stages of audio generation. The phonetic blueprint enters prosody generation to predict pitch and duration, creating a target specification. To implement these powerful speech capabilities, developers utilize the Azure Speech software development kits. The Azure Speech-to-Text and Text-to-Speech SDKs completely abstract the heavy lifting of network communication, secure authentication via Azure Key Vault or Microsoft Entra ID, and complex audio formatting. For a standard speech recognition client application, your Python code initializes the Speech SDK, captures audio directly from a local microphone or a streaming media file, and transmits it securely to the cloud. The Azure models run the inference and instantly return the transcribed text payload. However, modern AI architectures increasingly require real-time, interactive conversations with AI agents. This is where the Azure Speech Voice Live API is absolutely transformative. Voice Live enables true speech-to-speech capabilities. Instead of forcing developers to manually stitch together a speech-to-text pipeline, an LLM reasoning engine, and a text-to-speech synthesizer, Voice Live handles the entire real-time conversational loop through a single, highly optimized endpoint. When utilizing the Voice Live Python SDK, your application opens a persistent connection. It streams the user's spoken audio directly to the agent processes the intent and generates a response, and the service streams the synthesized audio back to the user's speakers simultaneously. Crucially, the Voice Live API manages highly complex conversational dynamics, such as handling interruptions when a user speaks over the agent, ensuring the application behaves exactly like a fluid, human-to-human interaction. By leveraging these SDKs within your Foundry projects, you can rapidly deploy intelligent, voice-capable agents without needing to manage the underlying microservices infrastructure. This drastically reduces development time, eliminates latency bottlenecks caused by round-trip API calls, and guarantees an incredibly smooth, natural conversational experience for your end users. To build a speech-to-speech agent, your code imports the Azure-AI Voice Live package. You initialize the client, hook it into the system's default microphone and speaker arrays, and open a real-time WebSocket connection. As the user speaks, the audio buffers are continuously streamed to Azure, and the synthesized audio response chunks are immediately streamed back and routed to the audio output hardware. This diagram maps the advanced Voice Live architecture. As we conclude our deep dive into AI speech workloads, we must examine the high-value enterprise scenarios these technologies enable, alongside critical governance considerations. Speech recognition is actively revolutionizing healthcare through clinical dictation, where doctors speak patient notes aloud, and the AI transcribes them directly into electronic health records, drastically reducing administrative burnout. In customer service, contact centers utilize real-time call transcription to analyze sentiment and ensure strict regulatory compliance. On the synthesis side, e-learning platforms automatically generate narrated lessons, scaling content creation globally without expensive recording studios. Furthermore, automated captioning and screen reading capabilities ensure that digital content is highly accessible to users with hearing or visual impairments. However, implementing speech AI responsibly requires strict architectural governance. You must always account for audio quality requirements, as poor microphone input or network degradation will severely impact recognition accuracy. You must ensure robust support for regional dialects and strict data privacy compliance regarding how voice recordings are stored. Most importantly, responsible AI guidelines dictate that you must always provide alternative input and output methods. Speech should enhance an application, not serve as a mandatory barrier. Thank you for joining this expert technical training session. To truly master these advanced AI workloads and accelerate your career, I highly encourage you to visit quicktechie.com for our premium certification prep. QuickTechie offers industry-leading Q&A banks, deep dive ebooks, audiobooks, advanced training modules, and expert interview guides. Build intelligently, innovate responsibly, and we will see you in the next lesson. By adhering to these best practices, your organization can confidently deploy AI solutions that are powerful, inclusive, and fully compliant. Join the community at quicktechie.com today to take the next crucial step in your cloud journey. Implementing inclusive design and code requires multimodal architecture. When designing your client interface, You must map the exact same backend agent execution functions to both the voice live audio streamer and a traditional text-based HTTP chat window, guaranteeing that users can seamlessly switch modalities based on their environmental constraints or physical requirements.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper. It would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now the third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepared for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.